Hi everyone, all of you guys are doing wonderful, and here we are starting with chapter 19. And in this chapter we're going to learn about ionic equilibria in aqueous systems, equilibria of acid and acid-base buffers, acid-base titration curves, equilibria of slightly soluble ionic compounds, equilibria involving complex ions. Acid-base buffers. So you guys may have heard about the term buffers before, but we're going to learn in detail about the acid-base buffers. Okay, so what is basically a buffer? Buffer is a solution that lessens the impact of pH from the addition of acid or base. Meaning, if you have a buffer system, you add acid and you add a base. You know, acids are less than pH 7, bases are more than pH 7. So when you add acid or a base, pH can drastically change. But if you have a buffer system, by adding a couple of drops of acid or a couple of drops of buffer, the pH does not change. Okay. So acid-base buffer usually consists of a conjugate acid-base pair, where both species are present in appreciable quantities in solution. In our previous lecture, we learned about conjugate acid-base pair. So hope you remember what are the conjugate acid-base pairs. For example, if you have acetic acid, right? Acetic acid is an acid, and then you react with water. So if you react with water, it is going to act as a base, right? So this is going to be your hydrogen that's going to donate as an acid, and then the lone pair of oxygen in the water going to grab this ionizable hydrogen and form hydronium ion and acetate conjugate base. So this is the acid, and conjugate base for acid is going to be acetate ion plus hydronium ion. So since this is the base, conjugate acid is going to be hydronium ion for water. So the conjugate acid base pair are going to be these two for conjugate acid base pair, right? So if you want to make a buffer with acetic acid, you have to select acetic acid, and also you have to choose a conjugate base for the acetic acid. Now from this acid, by looking at the acid dissociation of a weak acid, we make acetate ion from the solution. But in a buffer, we are not going to utilize this acetate ion as your conjugate base. We have to add it as a separate conjugate base. How would you do that? You're going to be adding this acetate ion in terms of sodium acetate. CH3COO, sodium acetate. Now earlier you had a hydrogen here, but the hydrogen now being replaced by sodium, so there would be sodium acetate. Okay, so basically if you want to make a buffer with this conjugate acid base pair, you would use acetic acid, and your conjugate base would come as the conjugate base sodium acetate. Okay, so why sodium acetate? Remember, since this is a weak acid, the dissociation is very less, right? Ka is a low number, so amount of acetate ion we are getting by this dissociation of the acetic acid is very less. But if you add sodium acetate to the system, meaning we have appreciable quantities. So we need to have both of these in appreciable quantities. Now when you add sodium acetate, what's going to happen is, since it's a salt, it's going to dissociate into ions, sodium ion and acetate ion. So in our conjugate acid base buffer system, you have acetic acid appreciable amount as well as acetate ion. So we are not depending on the acetate ion that generate as a result of dissociation of the weak acid. We are adding acetate ion on top of that. So we have both of these acid base pairs, conjugate acid base pair, in appreciable quantities in solution. That's how you normally make a buffer solution. Okay, so acid-base buffer is therefore a solution of a weak acid. So we chose a weak acid and its conjugate base, or it could be a weak base and its conjugate acid too. Okay, so we are using weak acid or weak base. Okay. Effect of adding acid or base to an unbuffered solution. Now let's say you have 100 milliliter of sample here, a dilute hydrochloric acid. It's not a buffer system. It has a pH 5. You add 1 milliliter of strong acid. What happened? When you add 1 milliliter strong acid, pH drops in 3 pH units. 5 goes to 2. Or you add 1 milliliter of strong base. Change the pH immediately, dramatically, going from 5 to 12. Right? 7 pH units difference. So it changes by several units. Obviously, this is not a buffer. Right? It's just a pH 5 acid. Now let's say you have a buffer system that we have adjusted the pH for 5. Let's say it's an acetate buffer. 100 milliliter sample of acetate buffer adjusted to pH 5. Then you add 1 milliliter, again the same amount of the strong acid. Look how much pH had changed, 0.02 units versus 3 pH units in the previous case, correct? So 5 goes to 4.98, and if you add a 1 milliliter of strong base, again it changes very little, 5.02, only 0.02 units. So you see the difference in a buffer and an unbuffered solution. So here we are adding the same amount of strong acid or strong base. 5 goes to 2, 5 goes to 12. 3 pH unit change, 7 pH unit change. Here only 0.02 because this is a buffer. Okay, that is the magic of the buffer. How buffers work? Let's see. Buffers and the common ion effect. So buffers work through the common ion effect. Acetic acid in water dissociates slightly to produce some acetate ion. Remember I told you earlier, acetic acid with water give you acetate ion and hydronium ion. To some, right? Because it's not a strong acid, it will give you some acetate ions. If sodium acetate is added, it provides a source of acetate ion. Now we are not going to depend on this acetate ion coming from the dissociation of acetic acid. You add sodium acetate. So that provides a source of acetate ion. And the equilibrium shifts to the left. Right? So when you add acetate ion, what's going to happen? Acetate ion with hydronium ion make acetic acid. So the equilibrium shift to the left. So acetate is common to both solutions. Meaning for the acetic acid, when it dissociates, it has acetate ion, and sodium acetate also provide acetate ion. So the acetate is common to both solutions. The addition of acetate ion reduces the percent dissociation of the acid. So when you have acetate ion already been added in terms of sodium acetate, so the acetic acid will not dissociate much. It reduces because it already has some acetate ion, so it doesn't need to dissociate. So the addition of acetate reduces the percent dissociation of the acid. Okay. Now let's say the effect of added acetate ion on the dissociation of acetic acid. Let's say you have 0.1 molar acetic acid initial concentration. You don't add any acetate ions. So the percent dissociation 1.3, pH 2.89. And this is the hydronium ion concentration. So let's say you add to the same concentration of acetic acid, you add acetate ion 0.05 molar amount. So the percent dissociation decreases, right? Because you have added some acetate ion. So if it decreases, what happened to the hydronium ion? Hydronium ion also going to decrease. What about the pH? pH increases. Remember, we have an inverse relationship between hydronium ion and pH. pH is negative log of hydronium ion. So more hydronium ion, less pH. Less hydronium ion, more pH. And you add more acetate ion. The more amount of acetate ions added, the degree of dissociation decreases. As a result, hydronium ions decreases and then the pH increases. Okay, so that's what this table shows. So how do you calculate the percent dissociation? We had talked about this before in our lecture also. The amount of dissociation, and you divide it by acetic acid initial amount times 100. That's how these numbers are being calculated. Sorry, these numbers, percent dissociation. Okay. Okay. So this just a table shows you as the concentration of the conjugate base more or increases, the percent dissociation decreases, hydronium ion concentration decreases, and then the pH increases. Okay. Relative concentrations of buffer components. So again, we are looking at our acetic acid with water giving you acetate ion and hydronium ion. We can write the Ka for this expression or the equation, acetate ions times hydronium ion over acetic acid. Right, that's the Ka, acid dissociation constant. So if you want to find out the amount of hydronium ion, basically what you do is you multiply Ka times acetic acid and you divide it by acetate ions. Okay, so this is a hydronium ion calculation. Since Ka is a constant, hydronium ion concentration of the solution depends on the ratio of buffer component concentrations. Remember, these two are our buffer component concentrations. Acetic acid is the acid component of the buffer, and then the acetate is the conjugate base component of the buffer. Now the acetate ion comes in terms of a sodium acetate. Okay, not necessarily the acetate that comes due to the dissociation of the acetic acid. Okay, so basically hydronium ion concentration depend on the ratio of the two buffer components, acid over conjugate base. If the ratio acid over A minus increases, if this ratio is high, what does it mean by hydronium ion concentration? It also increases. Right? If the ratio decreases, so then the hydronium ion concentration also decreases. Buffers and equilibrium. The buffer components HA, your acid, and the conjugate base are able to consume small amounts of added hydroxide or added acid by a shift in equilibrium position. Okay. Now, what happened when you add a little bit of base or a little bit of acid? How does it shift its equilibrium? Let's look at that. Now, this is our base equation where acetic acid with water, this is how we dissociate. It forms acetate ions and hydronium ions. Now, let's say you add hydroxide. You add a base to this one. Base is going to react with an acid in our buffer component. Okay, so remember our buffer component. So this is our acid in the buffer component, and this is the base, conjugate base in the buffer component. You add a little bit of hydroxide. Hydroxide is a base. If hydroxide is a base, when you add it, is it going to react with this acetic acid component or the acetate component? We know base not going to react, correct? So when you add a base, it's going to react with the acid component of the buffer. So added hydroxide react with acetic acid, causing, so if hydroxide going to react with this acid, which direction would shift the equilibrium? Equilibrium will shift to the right, right? Because it's going to react with acetic acid. So the equilibrium will shift to the right, right? So if you add hydronium ion is an acid. If you add acid hydronium ion, which one is it going to react? Is it going to react with the acetic acid or the acetate conjugate base? It's going to react with acetate conjugate base. So if it's going to react with this one, we are adding more of the product, so then the equilibrium will shift to the left, right? So the shift in equilibrium position absorbs the change in hydronium or hydroxide, and the pH changes only slightly. Okay, so since you have a conjugate acid, since you have an acid base pair in your buffer solution, whether you add an acid or whether you add a base, it's going to react with one of these components and shift the equilibrium. By doing that, it doesn't allow to have a huge change in the pH. So the pH will only change slightly. Okay, whereas if you have a solution without a buffer like hydrochloric acid, it's going to completely react, dissociate to H plus and Cl minus. So that those are not conjugate acid base pairs, and those are not in equilibrium either. So if you add an acid or a base, there are no components to react in a normal acid or a normal just the base. But if you have a conjugate acid base system, so this is how the buffer works. Okay, and then shift the equilibrium accordingly to adjust the shift. Okay, either to moving forward or going reverse direction. In this diagram also it shows how a buffer works. Let's say this is a buffer component that you have 50% of your acetic acid and also your buffer. Okay, so this is your A minus acetate buffer, A minus 1 2 3 4, and these are going to be your acetic acid 1 2 3 4. So 50-50 mixture, equal amounts. So you add hydronium ion to this one. Which one is it going to react? Is it going to react with acetate ion or acetic acid? Hydronium ion is an acid, it's going to react with the acetate buffer. So if it does react with this one, we are going to make hydronium ion and acetate ion going to make acetic acid. So the acetic acid amount going to increase. Since acetate ions have been used up, you will see it decrease a little bit, right? So then you will have 1 2 3 4 5 molecules of acid and 3 molecules of conjugate base. Similarly, if you add hydroxide ion, it's the base, is going to react with the acetic acid. So you're going to be making another acetate ion. Hydroxide is going to react with acetic acid, forming acetate ion and just the acetate ion, right? So then you will see acetate ion going to increase, hydroxide going to react with this one, acetate ion will increase, and we will see a decrease in the red one because you are going to react with this just slightly. Accordingly, the number of molecules will also change. You see 3 molecules of acetic acid and 5 molecules of acetate ions, like this. Acetic acid with hydroxide form acetate and water. Okay, water is not shown here. So buffer has equal concentrations of acetate ion and acetic acid, and this one has more acetic acid compared to acetate ions after addition of hydronium ion. And then after addition of hydroxide ion, buffer has more acetate ions. Okay, that is how a buffer works. So the pH didn't change much, just a little bit. It did change, but a little bit. Okay. Okay, calculate the pH of a buffer solution consisting of 0.5 molar HClO. Ka is given to us as 2.9 into 10 to the negative 8 and 0.6 molar sodium hypochlorite. Hope you remember the name of these oxyacids. Okay, so we want to calculate the pH. When do we need to calculate the pH? After adding 0.02 moles of solid sodium hydroxide to 1 liter of the buffer solution in part A. That's part B. And then the part C would be after adding 30 milliliters of 1.5 molar hydrochloric acid to 0.5 liter of the buffer solution in part A. In part B, assume that the addition of sodium hydroxide causes negligible volume change. Okay. First part is calculate the pH of a buffer solution consisting of 0.5 molar hypochlorous acid and 0.6 molar sodium hypochlorite. Now, do you realize now this is a buffer system because you have the weak acid HClO and then the hypochlorite anion given as sodium hypochlorite. Removal of the hydrogen gives us the salt. So this is a buffer component. So we want to first find out the pH of this buffer solution. Okay, let's see how we are going to find out the pH of this buffer solution. Okay, just like we've been doing earlier, since it's a weak acid, we will have to make a table, ICE table, ICE. So we use the given concentrations of buffer components as the initial values. Okay, we are given initial concentration of acid 0.5, conjugate base 0.6, and then we set up a reaction table, solve for X. Okay, and then X would be the amount of hydronium ion, and I will show you in the next slide. For B and C, we assume that added hydroxide or hydronium react completely with buffer to yield new initial values and then the acid dissociates. Okay, so let's go one at a time. Okay, here is our reaction. How the hypochlorous acid going to react with water. Hypochlorous acid with water going to give you hypochlorite ion and hydronium ion. Now initially, remember this is a buffer component. We are given initial molarity of acid is 0.5. So acid 0.5. Plenty of water, not to worry. And as a little different to what we have learned in the previous lecture or the chapter 18, this is a buffer system. So initially we would keep this 0 if it is just the weak acid, but since it's a buffer system and we are given the initial concentration of the conjugate buffer as 0.6, you're going to put it right there, 0.6. And hydronium ion still 0, right? So as the reaction proceeds towards the product side, X amount is going to react. Water, don't worry about that. And then X amount will be formed. And the X amount of hydronium ion also will be formed. That's the change. So in the equilibrium, what you are having is, so you use negative X amount, so 0.5 minus X. And then the hypochlorite ion would be, initially we had 0.6, and with this X amount that is being dissociated will be added to 0.6. So the equilibrium amount would be 0.6 plus X. And then the hydronium ion would remain as X. So our goal is to find out the hydronium ion because we want to find out the pH. Since Ka is small, so we can use the assumption X is small. So we assume 0.5 minus X, X is small, is similar to 0.5, and 0.6 plus X also equal to 0.6. Okay, so with that in mind, remember we came up with this ratio hydronium ion equals Ka times acid over conjugate base. We did this in one of the previous slides in this section. So then hydronium ion concentration Ka was given 2.9 into 10 to the negative 8, and HClO at equilibrium is 0.5 and ClO minus 0.6 right here. We use the assumption. So 2.9 into 10 to the negative 8, 0.5 over 0.6. That will give you hydronium ion concentration as 2.4 into 10 to the negative 8. What we want is the pH. Now, since we found the hydronium ion, we can check to see if our assumption is correct. How do you check the assumption? You take the X and you divide it by initial concentration, which is 0.5 times 100. So that is, you also do this calculation and see, you get the same answer, 4.8 into 10 to the negative 6. So which is less than 5%. So our assumption is justified, right? Once we justify the assumption, you can find out the pH. pH is negative log of hydronium ions, which is this amount. So 7.68. Okay. So this is how you would find out a pH of a buffer solution, if the initial concentrations of buffer components are given. So the next one, you are adding 0.02 moles of solid sodium hydroxide to 1 liter of the buffer solution in part A. Now, in part A, right, so you have that buffer solution and we can find out the concentration of sodium hydroxide, because concentration going to be moles over volume, 0.02 over 1 liter is going to be 0.02, right? Now we have to write another ice table. This sodium hydroxide reacting with one of our buffer components. Now you guys tell me, if you add sodium hydroxide, remember these are the buffer components. We have HClO and we have ClO minus. You are adding hydroxide. It's a base. Is it going to react with the acid component of the buffer or the base component of the buffer? Base doesn't react, right? So this hydroxide ion going to react with acid component of the buffer. So then what you're going to do for this part is you're going to react acid component HClO plus hydroxide ion. Okay, and then we have to develop an ice table for that. Let's do that again. So here you find your concentration, number of moles over volume, sodium hydroxide 0.02. So you take the concentration, initially HClO 0.5, you add hydroxide ions 0.02. So then you are making ClO minus, hydroxide going to react with this hydrogen to form water and ClO minus. And initially also we have 0.6 moles of hypochlorite ion that was given to us to begin with, right? And then the water plenty. And then the change is going to be, now we don't have to represent the change in X because we have acid 0.5, hydroxide 0.02. This is a small amount. So this, all of this hydroxide is going to react with the acid component. So the change going to be the amount of hydroxide ions. It's like acid-base reaction. So the change from this, you're going to be reacting negative 0.02 amount, and hydroxide also all going to react negative 0.02. Since it's 1-to-1 ratio, new amount of hypochlorite ion would be formed positive 0.02 amount. Now this amount is the change. At the end equilibrium, this will be added to the initial amount. Okay. So the final going to be initial minus the change, 0.5 minus 0.02. That would be 0.48. The difference, 0.5 minus 0.08. You started with this amount, you reacted this amount, nothing of hydroxide would be left. And this one would be, initially you had this amount. Now by reacting with hydroxide, you generated 0.02. So 0.6 plus 0.02 will make it 0.62 amount of hypochlorite ion. Okay. Now our goal is to find out the pH of this solution. By doing this part, what we did was we find out, after adding hydroxide, what are the concentrations of acid and the base going to be now. Okay, so after you do this part, you have to construct another ice table to find out the hydronium ion. Remember, hydronium ion gives you by this equation. Now using the initial amounts that we calculated after adding hydroxide, you're going to construct this table again, which is this. So setting up a reaction table for the acid dissociation using these new initial concentrations. Okay, as in part A. Dissociation is equal to hydronium ions. So concentration HClO plus water giving you hypochlorite anion and hydronium ion. Now our initial amount is what we have after reacting with hydroxide ions, which is 0.48. And then the perchlorite ion initial amount now 0.68. Hydronium ion 0. Now we're going to use the change as negative x, plus x, plus x. Equilibrium would be 0.48 minus x, 0.62 plus x. Since we are adding a hydroxide, a little bit of a base, do you think our pH going to be less than previously calculated 7.62 or more? What do you think? It should be less or more. We are adding a hydroxide. It should be a little bit more, right? Okay. So now we're going to calculate hydronium ion with the same equation, making the assumption that x is small and solving for x. 0.48 minus x equals 0.48. For 0.62 molarity plus the x amount also 0.62. So hydronium ion concentration, we use the ratio along with the Ka, acid component of the buffer divided by the concentration of the base. Acid component 0.48 divided by 0.68 times the Ka. 2.2 into 10 to the negative 8. Calculating the pH, negative log hydronium, which is 7.66. Since we added a base, it increased just a slight amount. Addition of a small amount of base caused the pH to rise only slightly from 7.62 to 7.66. Okay. It looks like more steps, but if you understand it, it makes sense. Correct? So you can revisit this part and see how we got that value. And then the part 3, after adding 30 milliliters of 1.5 molar hydrochloric acid to 0.5 liters of the buffer solution in part A. Now here the part B, we add sodium hydroxide. Now we are adding 30 milliliters of 1.5 molar HCl to 0.5 liter of the buffer solution. Okay. Now we have to calculate the molarity of hydrochloric acid, and then again you have to see which component of the buffer hydrochloric acid going to react, right? Let's say I'll show you how to calculate the hydrochloric acid, but again these are our buffer components. You are adding HCl, hydrochloric acid. So this is the acid component of the buffer, this is the base. Adding hydrochloric acid, which one is it going to react with? Acid will react with this guy. Just like we did with the hydroxide ion, you have to write do the ICE table and then find equilibrium concentrations and use that to construct the second ICE table to find out the pH. Okay, let's do that. Okay, calculating the volume. The new volume is, now you are adding 0.03 liters of the hydrochloric acid to 0.5 liter of the buffer solution. This was given in the question. So 0.5 is the buffer solution. 30 milliliters of hydrochloric acid, converting into liters will make it 0.03. So the total volume, new volume is 0.53 liters. Okay. Now we have to calculate the initial concentration of the acid, because now the concentrations have changed since you added a 30 milliliters. So we can use M1V1 equals M2V2. M concentration times V concentration equals molarity of the acid times the diluted volume. So the diluted concentration would be concentrated solution molarity. Remember, it was 0.5 molar given to us. So if you have forgotten, we can refer back to here. Initial concentrations, remember, 0.5 molar acid and 0.6 molar base. Remember this also. Okay, 0.6. So 0.5. I hope you remember the M1 V1 equals M2 V2, or you can also use the concentration and the diluted terms. So the M concentration is the molarity of the acid, which is 0.5 given to us, and then the concentration, not the concentration, the volume of the concentrated solution is 0.5 liters, 0.5. And then the diluted solution, since we are doing a dilution, the volume is 0.53 liters. So you divide by 0.53. That will give you 0.47 molar acid solution. Similarly, if you want to find out molarity, new molarity for hypochlorite ion. So that would be, again you can follow M1V1 equals M2V2. So if you do that, that would be ClO minus concentration would be, there was 0.6 molarity times the volume 0.5 over diluted volume 0.53. That will give you 0.57. Can you do that calculation and see if you get the same number? 0.53. Yes, 0.566. That's how you calculate this value. Okay. And then the hydronium added, because you're adding hydrochloric acid. Again, the concentration of the hydrochloric acid, how to calculate this amount? This would be, I think it was 0.15, isn't it? I believe it was 0.15. 1.5, right? So 1.5 times volume 0.03, and then you divide by new volume 0.53. That will give you hydronium ion concentration, again using the dilution equation. 1.5 into 0.03 over 0.53, 0.0849. So 0.085. That's how you calculate these values. Okay. Now you use that in our table. Initial concentration 0.57, we calculated. Hydronium ion concentration 0.085, and HClO initially we have 0.47. Okay, and then the change going to be, now hydronium ion going to react with conjugate base. So that's why we wrote our equation like this: hydronium plus the perchloride hypochlorite anion. Since we have 0.085, it's a small number, it's all going to react with this conjugate base. So you use that amount, same amount of hydronium ion, and 1:1 ratio, you are making positive 0.085, right? So the final going to be 0.57 minus this amount 0.448. All of this would be used up, and then you add these two together to find out the final concentration of HClO. Now with these initial amounts, we write again, just like we did with the hydroxide ions, we do the acid dissociation, weak acid dissociation, using these new initial amounts. 0.56 hypochlorous acid, and then hypochlorite anion, new amount is 0.48, nothing of hydronium ions formed. You're going to put your change as X, positive X, the difference 0.56 minus X, and then we using the Ka, we're going to find out hydronium ion concentration using our assumption. 0.56 minus X equals 0.56, same thing, plus X equals the same amount, and then the X going to be hydronium ions Ka acid over conjugate base. So the acid amount 0.56, base 0.48. Find out your hydronium ion concentration, and then you can also check to see if the percent dissociation is less than 5%, that would be less than 5%. And then the pH would be negative log of hydronium ion 7.47. Now since we have added acid, the pH slightly changed from 7.62 to 7.47. Okay. So this is how we also calculate the pH after adding acid or a base to a buffer system. And also you saw that the change is very slight, only 0.0 something amount. Okay. Okay, so we can stop our session here.